All right. We will start getting into some calculations today, but I do need to define a few more things before we get into that. Um, so the first three terms that we're going to hear a lot in this class are states, properties, and processes. Um, so the easiest, shortest way to think of it is a state is a collection of processes. Um, sorry, state is a collection of properties. And a process is the transition between two states. Um, okay, so a property is just a thing that describes whatever you're isolating, whatever thing you're looking at a single instant. Um, so your isolated system at an instant. Um, so for example, if your isolated system is, a collection of gas molecules, you can describe it using its volume, its pressure, its temperature. Those are all things that describe the gas at that instant. Put all of those things together, and there's infinitely many of those things. You could describe it, its color, its whatever. You could think of a lot of ways to describe it, but all of those together describe the state that it's in. So all of those together give a full description of the object at that instant, or the system at that instant. Okay, so let's go through sort of an example, something, the kind of thing that we'll be dealing with. So let's say that we have a gas, initially has pressure of 2.0 times 10 to the 5th pascals, a temperature of 350 Kelvin, and a volume of 0.6 cubic meters. then it's compressed to a pressure of 3.0 times 10 to the fifth pascals. Temperature of 400 Kelvin. And we're compressing it so the volume have to be a little smaller, let's say 0.3 meters cubed. Okay, so what are the properties? What are the states? What are the processes? So let's say that first state, that first instant that we have information about is state 1, and the other stuff is state 2. So state 1 is made up of a pressure of 2.0 times 10 to the fifth pascals, a temperature of 350 Kelvin, volume of 0.6 cubic meters, and on and on. Those are the only ones that I gave, but you could describe a million more things about it. So these are properties. And then state 2 has the pressure of 3.0 times 10 to the fifth pascals, the temperature of 400 Kelvin, the volume of 0.3 cubic meters, and a million more things you could describe. These are all properties. And the process is the transition going from state 1 to state 2. So this is the process. The equations that we're going to use in thermodynamics do two things. One, they can be equations of state, and those are relationships between different processes at an instant. An example of this is the ideal gas law. It's just looking at different things that are going on at a single instant, and it's saying, the form that you're probably most familiar with is pressure times volume is equal to N times RT. For us, this R is going to be our over bar. I'll talk more about that in a second. So that doesn't tell you anything about what's going to happen 20 seconds from now. It just says right then, if you know the pressure and you know the volume, you can calculate the temperature, or if you know any two of those, you can calculate the other one. And the other kinds of equations will have tell you what happens during processes. So what are the restrictions on the states that can occur under certain conditions? Examples of these are the first law and second law of thermodynamics. The first law of thermodynamics is conservation of energy, so I'm going to write it like that now. But, you know, properties and states and processes, those don't only relate to, I mean, we only use those ideas in thermodynamics, but really, I mean, you could apply that to anything that you've talked about in physics or engineering in the past, you know, like when you have a problem where someone's up on a skateboard at the top of a hill, at state 1, they have the property of being, you know, 10 meters up above the ground, and they have the property of having 0 velocity, and on and on. And once they come down the hill, they have, at a different instant, a different state, they have the property of having 0 height and the property of having a velocity of 15 meters per second or something. And we used, to do problems like that, to figure out what the speed was or whatever, there's no way they could go down a 10-meter hill and be going, without other forces applied, and be going 400 miles an hour. You know, we figured out that they were going 15 meters per second. That's just the arbitrary thing I said, by applying conservation of energy. And conservation of energy says, if they're down at this height, we know their speed has to be, you know, this set thing. So that's sort of how processes, states, properties apply to stuff that we've done before. So let's break up properties. They come in 2 types. Those are extensive and intensive. Extensive properties are only defined for a set amount of material. So they're only defined for, or let's say, a chosen amount of material. And the real test of whether something is an extensive property is if you break the material up into pieces, however many pieces, and I'm not talking about physically pulling it apart, just, you know, separating it up into what you're calling piece 1 and piece 2. So let's say here's the system. So this is this represents a state, and we'll break it up into, it doesn't matter the shape of these sections or anything, but I'll call this S1, S2, S3. If P is an extensive property, then that property, as applied to the whole thing, let's call this whole thing state S. That property over the whole thing is equal to that property for S1 plus that property for S2 plus that property for S3. Okay, so it has that additive thing. So let's think about a couple of different properties and see which ones are extensive, which ones are not, okay? So first of all, think about mass. Is mass extensive or not? Yeah, so if the whole thing is 10 kilograms and S1 is 2 kilograms and this is 4 kilograms and this is 4 kilograms, they have to have this additive relationship. Now think about temperature. Is that extensive? No, you know, they could all be, so if it's 50 degrees Celsius, 50 degrees Celsius, 50 degrees Celsius, the whole thing doesn't have a temperature of 150. Examples of extensive properties. Are the mass, and we represent that as a lowercase m. The volume, represent that as a capital V. The area, you know, maybe you're talking about a surface of contact or a surface area that, you know, where two different bodies are in contact. That's capital A. Almost always, properties be represented by capital letters, but you can see mass is, I think that's the one example I can think of that that's represented with a lowercase. Extensive properties are represented by capital variables. Okay, intensive properties are anything that aren't extensive. And those are ratios of an extensive property divided by some, I guess it's a ratio of two extensive properties. Don't write that down. That's off the top of my head. But they are properties measured per. Okay. So some examples. Of intensive properties. Are density. That's represented by lowercase Greek letter rho, like a sort of scripty P. And SI units of density. Anyone remember what density is? Yeah, mass over volume. So yeah, that would be like kilograms per cubic meter. Specific volume, this is one that you probably haven't used much in classes outside of thermodynamics, but this is one that's going to be important to us. That's represented as a lowercase v. And it's just 1 over the density. So that's volume over mass. Pressure. We'll write that as a lowercase p. And that's a force over an area. So that's newtons per meter squared. That's equivalent to pascals. And then temperature, you know, the way we're used to thinking about temperature, that's not really a ratio, but what temperature really measures is like sort of an average kinetic energy, and so you can think of it as like an energy per mass. But we'll represent temperature as a capital T, and in SI units, that's degrees Celsius or more often Kelvin. Intensive properties are almost always represented by lowercase variables. When we were talking about extensive properties, mass was the exception. When we're talking about intensive properties, temperature is the exception. Intensive properties with a overbar mean that they're measured per mole. Per mole of material. So a mole is just a quantity of material, a number of molecules, a number of atoms, and just like you could measure the mass per, well, just like you could measure the volume per unit of mass, you could measure the volume per mole. It's just another way of breaking it up into a total amount. And so, for example, if you have a lowercase v with an overbar like that, that's equal to volume per mole. Also, the universal gas constant, that's a capital letter, but that is, anyone remember what the SI units are for the universal gas constant? Joules per mole times Kelvin. Or, you can think of that as joules per Kelvin per mole. And if you think about it that way, that's measured on a per mole basis. And so we're going to represent that with a overbar. Okay. The gas constant we're going to use more often is the universal gas constant divided by the atomic mass of whatever molecule we're using. So it won't be measured per mole. All right, any questions about that? So let me say a couple things about temperature, and then I'll say more about pressure. And with pressure, we'll get into our first sets of calculations. Temperature. Temperature is a pain in the butt for one reason. If you sit on something hot, okay, two reasons. If you sit on something hot, then figuratively it's a pain in the butt because you have measurement scales that don't have zeros in the same place. No other units that we deal with have that. Okay. That causes headaches. So that can be difficult because there are commonly used, common units don't agree on what zero temperature means. Okay, so what that leads to and this is the only, these are the only units that you have to worry about this with. When you're dealing with temperature, you have to be very clear on whether you're talking about a change in temperature or an instantaneous temperature as a property. Okay, a change in temperature, like if you're talking about how much is the temperature going to rise today, you have to think about that differently than what's the temperature at this instant. Changes in temperature have to be treated differently than instantaneous temperatures. Okay, so the 4 temperature scales we're going to use are Celsius, Fahrenheit, Kelvin, and Kelvin is Celsius, except that it's the zero temperature in Kelvin is at absolute zero. So this is the same scale as Celsius. But zero is at absolute zero. And then one you don't see as often, but it's the same. It's like the Kelvin for Fahrenheit scale. It's called Rankine. And it's the same scale as Fahrenheit. Zero is an absolute zero. Okay, so like I said, we have to differentiate between, so if everybody just used Kelvin and Rankine, then that would be the easiest thing. But we don't get to control that because, we have to, other people are going to give us measurements and we don't control what they've measured in. And so we're going to often have to convert units, and we have to have two different ways of converting units. One is if we're converting instantaneous temperatures, and one is if we're converting changes in temperature. So unit conversions for instantaneous temperatures. So the temperature in degrees Fahrenheit is equal to a Rankine temperature minus 459.67. The temperature in Celsius is the temperature in Kelvin, and for some reason Kelvin is the one that you don't use a degree sign. Minus 273.15. And then the temperature in Fahrenheit, degrees Fahrenheit, is equal to, nope, these are different scales, 9/5 temperature in degrees Celsius plus 32. If you're dealing with changes in temperature, so unit conversions for changes and let's say the change in temperature in degrees Fahrenheit is equal to the change in temperature in degrees Rankine. The change in temperature in degrees Celsius is equal to the change in temperature in Kelvin. And the change in temperature in Fahrenheit is 9/5 the change in temperature in degrees Celsius. So the constants go away. It makes sense if you think about, think about what would happen if you didn't have, if you use those additive constants in a, when you're talking about changes in temperature. So if it's if it's 0 degrees Celsius, it's 32 degrees Fahrenheit at an instant, right? But what if the temperature, like somebody told you the temperature went down 5 degrees, and you say, they say 5 degrees Celsius, the temperature reduced, it got colder, 5 degrees Celsius. If you still use this additive constant, you take 5, you'd get, negative 9 degrees plus 32, and that would tell you that in Celsius it went down 5 degrees, in Fahrenheit it went up 22 degrees or 23 degrees or whatever that is. That doesn't make any sense, So when you're talking about changes in temperature, those constants go away. Any questions about that? All right. So now we're going to talk about pressure. So you can talk about pressure with solid bodies, but it's a lot more useful, a lot more applicable to fluids. It's mainly applicable to fluids, and fluids are liquids and also gases. And also supercritical fluids, but we won't talk about that now. So, like when you take classes in fluid dynamics, you'll be talking about stuff that applies to liquids and applies to gases. So aerodynamics, when if you're talking about airplanes and stuff, you're talking about the motion of gases as it goes past an aircraft or whatever. That's still a part of fluid mechanics. Pressure is the force per surface area that the fluid applies perpendicular to its boundary. Okay, so for example, if you have this enclosed vessel, there's some gas out here, some gas in here. The gas on the inside at every location on the boundary is applying a force per area perpendicular to that point on the boundary. And all it can do is push out. It can't pull in. What that means is that suction is not an actual thing. I mean, it's a reasonable way to think about, but so notice suction doesn't really exist. What seems like suction is actually a mismatch between pressures on two different sides of a boundary. There's only two different pressures fighting against each other. Okay, so like, have you ever noticed that uh, if you order like a bag of chips on an airplane or something, it always looks like it's inflated? Um, Airplanes are pressurized. Otherwise, you'd have to hold your breath the whole time. Um, but they're not pressurized all the way to atmospheric pressure. They're pressurized to the equivalent of like 10,000 feet of altitude, just to save effort and money and whatever. Um, and so these potato chip bags are sealed at sea level at atmospheric pressure. At atmospheric pressure, they look like normal chip bags. And they look like normal chip bags because when they're sealed, the air pushing in at the boundary perpendicularly to the surface is at atmospheric pressure. And the air pushing out exactly counteracting that is at atmospheric pressure. So neither one of them is winning, you know. But when you go up to 10,000 feet of altitude, the air on the inside can't get out. It's still at atmospheric pressure. The air on the outside is weaker now. The pressure is lower. And so now that battle is being won by the pressure on the inside, and the bag looks like it's inflated. It used to be that airplanes' baggage holds didn't have weren't pressurized at all. You know, they were underneath, and so if you talk to older people, you know, like you would forget to take like the shaving cream or something out of your toiletry bag, and you'd get there and it would have exploded because you have atmospheric pressure on the inside, a tiny amount of atmospheric pressure pushing in, and now it just explodes the thing. That's what would happen to a chips bag if you put it at, you know, if you brought it to Mount Everest, 30,000 feet up, it would explode. So what's going to be useful to us, so now this is our first calculation, our first tool for calculations. If a fluid um, is continuous and at rest, then so let me draw a picture of this. Okay, so here's a continuous fluid that's obviously like a totally arbitrary shape. And let's say that this is point 1, and here we have pressure P1 and height H1. And this other point we'll say is over here, and at that point we have pressure P2 and height H2. And the difference between those we'll call H. So if all the fluid inside here, you know, say this is air or some other gas, it's continuous and it's at rest, then the pressure P1 minus the pressure at P2 is equal to rho times G times H. So this is the pressure at the higher point. Nope, lower. P1 is the pressure at the lower point. P2 is the pressure at the higher point. Rho is the density of the gas. G is the gravitational constant, wherever you are. So at sea level, this is 9.81 meters per second squared. It'd be something else if you're doing this on the moon or whatever. And h is the difference in height. What does that say about the pressures of 2 points that are at the same height? They have to be the same. Okay, so if you have a continuous fluid that's at rest, the only thing changing the pressure is changes in height. Question? In terms of height, yeah. Okay, so question. So here's an inner tube, it has a pressure. There's an atmospheric pressure out here, and the pressure inside the inner tube is greater than the atmospheric pressure, even at the same height. How can that happen, according to this? Like, what are the conditions of this? That's what I'm just asking about the conditions. This is at the same height, How can that be? Well, it's because the gas isn't continuous. The inner tube boundary separates those two completely. If you take a pin and put a hole in that boundary and make the air continuous and wait for it to come to rest, then eventually it'll be the same pressure. And the same thing can happen with if you're forcing air through. So, and how can this happen? Probably can guess the answer already, and I haven't even drawn the picture yet. But say you're forcing air through a tunnel that has a shape like this. Okay. So air is going this way. When it's here, it has a low pressure. When it's here, it has a high pressure. It's back to here, it goes back down to a low pressure. Those are all at the same height. How can the pressures be different? It's not at rest. Okay, there's two main ways to measure pressure. The first one is called a manometer. And you use this for measuring the pressure of a gas inside an enclosed area. Enclosure. And the setup looks like this. So here's the enclosure. I'm drawing it like a round bulb. And then you have a tube that goes like this. And then back up, and it's exposed to the atmosphere. So up at the top, right here, if this tube is open to the atmosphere, what's the pressure at the top of the liquid there? Red is a liquid. What? Yeah, right. So this is the atmospheric pressure. So I'll call that PATM. And this is where we want to calculate the pressure. This red is a liquid with a density of rho. And so this distance here is, we'll call that h. So you measure the difference between those two heights. And then P minus PATM is equal to the density of the liquid times 9.81 meters per second squared times h. So you're trying to find that P, you know what the atmospheric pressure is. So P is equal to PATM plus rho GH. The second one is called the barometer. And you use a barometer to measure atmospheric pressure. And that looks like this. You have like a dish, and liquid can go from this dish up into a tube that's enclosed at the top. And then you have a liquid that sits in the dish. And because the dish communicates with the tube, it can climb this tube. We're going to call this distance h. The red is a liquid with a low vapor pressure. Whatever temperature you're doing this at. Mercury is a good choice for this. And this liquid has a density rho. Okay, so the reason you want a low vapor pressure is the pressure up here in this, like up above the liquid in this tube, the pressure there is the vapor pressure of this liquid. So like if this was water and you were doing this test close to the boiling temperature, water really wants to, close to the boiling temperature, water really wants to evaporate, you know? And so you'd have a pretty high pressure up there, and this would throw this calculation off. But at room temperature, if this is full of mercury, mercury pretty much wants to stay liquid at room temperature. There's not a lot of mercury shooting up into the air trying to turn into gas. And so you can approximate the pressure here as 0. Okay. So here you have a pressure, and if you didn't want to use mercury or something with a low vapor pressure, you could calculate the vapor pressure, look it up, and the pressure up here would just be that vapor pressure. But it's easier if you can just treat it as 0. So I'll write this as T vapor, we'll call it about equal to 0. And then this is just a dish. So what's the pressure on the liquid at this surface? Atmospheric pressure, yep. And so P atmosphere minus P vapor, and I'm going to say this goes away, is equal to the density of the liquid, the mercury, times G times H. Any questions about that? Okay, let's do a couple calculations. So let's say that we have an enclosed vessel, and the setup goes like this. And let's say that this liquid is water. And the difference in height between two ends of that column of water is 0.80 meters. The density of water is 1,000 kilograms per cubic meter. What's the pressure of the gas inside the vessel? And assuming that the atmospheric pressure is, well, if we're right at sea level, it's 1.01 times 10 to the 5th pascals, so let's go with that. Okay, so why don't you take a couple minutes and see if you can work through this. Feel free to talk to each other, ask me questions if something's confusing, and then I'll do it in a minute, okay? But this. So This is a manometer. We know that the pressure at the top of the liquid on the left side that's the pressure we want. Up here is atmospheric pressure. So P minus atmospheric pressure is equal to the density of water times 9.81. I'm doing all this in SI units. Times the difference in the heights of those two, so 0.8. And so the pressure of the gas is 1.01 times 10 to the 5th plus, I can do this in my head, watch this. 800, that's 7, 8, 4, 8, right? Yes. Take that, Dad. You said I'd never amount to anything. What's that? 100, that's like 1.08, is that right? 848 times 10 to the 5 pascals. I don't care. Yeah, I don't care about that. No. Well, I mean, yeah, I mean, if you do it right, I don't care. If you want to give that answer as 100,000 or whatever, I guess that's fine with me, just as long as you do the steps right. Yes. That what? Yeah, that's right, because the top of this tube is open. You know, so that's the key difference between these two. At the top of this tube, it's open, so that is atmospheric pressure. In the barometer, it's closed, and so that pressure is different, you know, vastly different from atmospheric pressure. Okay. Yes. Yeah, sure. Yeah, so let's think of, so pressure is, that's, I'm going to just go back to like the basic units of everything. So pressure is newtons per meter squared. Newtons is kilograms, meters per second squared. So that's newtons, and then divided by meters squared. So you cancel that. And so this is our unit for pressure, is kilograms over second squared times meters. And on the other side, we have density, which is kilograms per meters cubed, times acceleration, which is meters per second squared, times a distance, a length, so that's meters. And so those 2 meters cancel 2 meters from that, and they come out the same.
Unrealistically high outside of it.
Mm-hmm. Yeah. No, as long as your tubes are long enough. If you get to the horizontal part, then if you get to the horizontal part, yeah, I think it would work perfectly fine unless you got to the point where like once that gets horizontal, then it flattens out and would just drip into the, so that would be the problem. So it just, these two lengths have to be long enough that it doesn't squirt out this end or drip into there. Yes. Yeah, you could for sure. Yeah, and it doesn't change the calculation at all. So that just says that because if you did that, your H would be negative, and your H would be negative, and so yeah, the calculation would still work perfectly well. Okay, let's do one with a barometer. Okay, so let's say we have a barometer set up. We're going to assume that the pressure up here is 0. Let's say that this distance is 0.55 meters. And let's say that the red is mercury. So the density of mercury is 13,690 kilograms per cubic meter. What's the atmospheric pressure? Okay, so see if you can work through that one in a couple minutes. Okay. So this is a barometer. And we know that the lower pressure, that's the atmospheric pressure that we're looking for, minus the higher pressure, which we're approximating as 0, is equal to 13,690 times 9.81 times 0.55. And so the atmospheric pressure is 73,864 pascals. That's newtons per meter squared. At sea level, atmospheric pressure is 101,000 pascals. So this would be, significantly above sea level to have an atmospheric pressure like that. Any questions about that? Okay. Well, I'll, I guess by tomorrow morning sometime, I'll put an assignment up that I want you to try to finish by class on Tuesday. And remember, you're not going to turn it in. You're just going to put it in your binder, and then I'll check everything when I pick up your binders. And remember, there's no school on Monday. So if you drive all the way over here and it's locked, you'll be mad.